Okay, so today we're going to talk about gravitational potential energy. So what I want you to do is make sure you pause the video when I ask you to pause the video because you're going to learn so much more that way. So first what I want you to do, go ahead and write down your equation for gravitational potential energy, the normal equation we've used all year. Okay, so the normal equation we've used for gravitational potential energy is just mgh. Okay, where m again is the mass, g is acceleration due to gravity, and h is the height above where we are. But okay, now when we're dealing with planets and like big old distances, so let's say I have a little planet right here and I have another mass right here. We're not going to be able to use this equation as, let's say, this mass changes from like the surface of the planet to all the way up. Why is that? I want you to think about that and write down a guess. Okay, so after you've thought about it for a couple minutes and written down a guess, we'll chat about it now. So let's think about it. Is this acceleration due to gravity from the surface of a planet to way up here constant? No, it's not constant at all. It is changing so much. So we're going to have to use a different equation for UG now. So this new equation that we're going to use. Okay, so again, this is the equation we're not going to use. We can't use because acceleration due to gravity changes. Due to gravity changes, and it is not constant. And when things aren't constant, we have to deal with calculus ideas, whole new ideas. Okay, so now let's say we have some mass, this little mass m1, and we have a planet of mass m2. They are separated a distance of r between them. And again, that is a center to center distance. So this new equation for Newton's law of gravitation for gravitational potential energy is UG equals negative G m1 m2 divided by r. And again, r is the center to center distance. Center to center distance between the objects. So keep that in mind. R is the center to center distance between the objects. And this is the equation we are going to use now that we're dealing with really big distance and planets, really massive objects, and where r is really big. Cool. And I want you to think too, like these two masses, m1 and m2, whatever they are, m1 and m2, have some gravitational potential energy between them. So keep that in mind. Okay, so now what I want you to do is go ahead and just take a guess. If we were to have a function and we were to graph the function u, so gravitational potential energy based on r, I want you to guess what that graph would look like, and then check back in on the video. Okay, so after you've done the graph, let's chat about it together. So we know, so g is a constant, that's always 6.67. m1 and m2, those are constants of two things, so that's just a constant. So our equation is essentially negative a constant over r. Okay, so, and this constant's always positive. R will always have a positive number. So u is always going to be negative. So we are dealing with something down here when we think about our function. And it's essentially 1 over r, which we know that'll graph like this. Okay, so let's go ahead and think about this, a couple things. So when r, and go ahead and write this down. So when r is approximately 0, u is how big? It's like negative infinity big. Yeah, okay. And let's think about that. Does that make sense? Okay, so at this point right here, it is impossible for two objects to occupy the same space at once. So this can't actually happen in real life. So it's like a super essentially small potential energy because the objects are basically on top of each other. And this can't happen in real life anyways. So this is a really small potential energy, almost no potential energy if they're on top of each other, which makes sense because there's no separation between the two objects. So U is super small. Okay, so now let's look at another instant. So let's say if R equals really big, so let's say it's close to infinity. So if R is super big, close to infinity, it looks like U approaches 0. Okay, so, and I think about this, if two objects are infinitely far away, so they're infinitely far away, they can have no potential on each other. There's no potential that they will interact with each other, and there's no potential energy. So oftentimes you'll see written in AP physics problems or any problems, for that matter, is U is, and again, U is defined as 0 when infinitely far away. When infinitely far away. And that does not mean the potential energy is always 0. It just means when the separation between the two masses, M1 and M2, are infinitely far away from each other, the potential energy is defined as 0. And you'll see that written in problems all the time. Cool. The last thing I want to chat about is, okay, it is kind of funky that potential energy is always negative. And it's just how this function works. We don't necessarily care about like a positive or negative quantity. We just care about how something changes. So if something changes from going like, closer together, or sorry, where R increases, so it's like R increases to like starting off here, it's going to be like a positive change. So keep that in mind if we're doing the change. That's what really matters. Okay, we're going to do another little thing. Okay, so now we're going to go ahead and go to part 2. We're going to think about energy of satellite in motion, and we're going to think about elliptical orbits. Okay, so let's go ahead, and what I want you to do, look at this whole thing. We have an elliptical orbit and we have a circular orbit. Go ahead and answer questions 1 through 3 for each of them. Pause this video and then check back in and see what you got. Okay, so compare total mechanical energy. Again, total mechanical energy is just a fancy word for total energy. And this is energy that can be like reused, so not friction energy, which is like dissipated to the environment. Okay, so if it's in the same orbit, what do you think is going to be true about the total energy? It is just going to be the same. So the total energy is constant. So total energy at A, B, and C is the same. Okay, so now let's think about it. The KE of a satellite positions A, B, and C. So think about the video we watched the other day where something orbiting around. When it goes closer to the Earth, whatever that is, whether it's a planet, satellite, whatever, something orbiting around something, there's more gravitational pull and it is going to speed up. So the KE at A is going to be biggest, while when something is farther away, it is going to have less kinetic energy. Cool. So now let's think about potential energy. So where is something the biggest? So it has more potential energy when it's farther away. So the potential energy at C is going to be greater than the potential energy at B, which is even greater than potential at A. Cool. So that's pretty conceptual. I like that. Okay. Let's go ahead and look at this one now. So total mechanical energy of the satellite in orbit 1 and orbit 2. So if we think about, and we could prove this with numbers, I'm not going to go ahead and do that now, but if something needs to go from orbit 1 to orbit 2, it's going to need to burn some fuel. So it's going to need to burn fuel, or essentially like we're going to need to put more energy in the system. So orbit 2 is going to have more energy, total energy, than orbit 1. Okay, so let's go ahead and look at the last one. Which orbit will experience greater force of gravity? Okay, so greater force of gravity, again, we know our equation for force of gravity, sorry about the bad writing, is Gmm over r squared. And let's see here, so that is our force of gravity equation. And if G and the two masses are staying the same, r is the only thing that matters. So the closer you are, the more force you'll experience. So we'll say orbit 1 will have a greater force than orbit 2. Cool. Now let's think about which satellite will be moving the fastest. And in class we discussed a lot of awesome things. I loved what like Nathan said and lots of other people said about this. But orbit 1, okay, if you're pulled inward, so the Earth has more of a pull in orbit 1, you're going to go faster because of that. So orbit 1 is going to be greater than orbit 2. And I think of it too, you could derive it, but F net C we know is equal to force of gravity. You can use that to solve for velocity and prove that in orbit 1, you're going to be going faster than orbit 2. Cool. We're going to go ahead and do one problem together. Okay, so again, I would encourage you to try this problem yourself and then check back in on the video after you do that. Okay, so let's go ahead. First thing we always do with these problems is go ahead and draw a picture. So we have a satellite of mass m. It moves an elliptical orbit around Earth. Okay, so the mass of the Earth they're saying is m. Then we have the satellite's elliptical orbit. Now we're not dealing with circular orbits. We're dealing with elliptical orbits. Okay. So So we cannot, since we're dealing with elliptical orbits, again, we cannot use F next to E. That is only for circular orbits. Okay, with R and R, the closest and farthest distance from the Earth. So this is going to be R. Oh, and it's the center of Earth, even better. Great. And then this is going to be big R. So here it is at those 2 points. Okay. And it has total energy. And again, total energy, we know as it stays in elliptical orbit, is constant. So total energy is constant. So it'll have the same energy at this point as it does at that point. Cool. So determine the speed of the elliptical satellite at closest approach distance. So we want to find velocity here. Okay. So what do you think about when things are changing positions? Okay, changing positions and changing speeds. We're going to use energy conservation. That is going to be our best bet. So let's go ahead and think about this. So we have E total. Oh, no. I should just label just to start. Energy conservation, changing positions. We got it. Okay. So let's go ahead and label what type of energy it has at this point where its distance are. So it's some distance from the center of the Earth. So we're going to know it has gravitational potential energy. And it also has kinetic energy. It's moving. So it has those 2 types of energy. Again, it would have the same, just different amounts at this other point too, but we're only really caring about this point right now. Okay, when we think about UG, now we have 2 equations, remember, mgh and gmm over r. In this case, it is way far from the center of the Earth, like that little acceleration due to gravity is changing from all the way out here to all the way to the center of the Earth. So we're going to have to use our special new UG equation. Okay, so let's go ahead and look at it. So the total energy, so energy at point R, because that's the point we're looking at. We could compare these 2 points, but I don't know the speed at this other point with big R. So, but I know the total energy. So E total is going to be the sum of our gravitational potential energy plus our kinetic energy. E total I know is negative gmm over 6r. Weird thing is, we're all dealing with negative quantities for this energy just because UG is defined as a negative. And this is gmm over r is the distance from the center of the object to the center of the other object, which is just r in this place, plus what? 1/2 mv squared. Again, we want little m because we're dealing with little m, not the big M of the Earth. Okay, so now let's go ahead and solve for, let's solve for the velocity. So let's see. I want this term dealing with velocity on its own side, so I'm going to rewrite a couple things. So this is just rewriting the term above over r. I just pulled out the 1/6. I'm going to add the gmm over r to the other side to cancel it out. And then we're left with 1/2 mv squared. Okay, so now it's like I have negative 1/6 of this whole thing, plus this is just essentially 1 over 1, which I could call 6 over 6 to have a common denominator. So this is negative 1/6, but 6 over 6, so that's going to be what, 5/6? So that's what, 5/6? Yeah, positive 5/6 gmm over r equals 1/2 mv squared. Cool. Let's see. I'm going to want to, oopsies, I'm running out of room. Sorry about that. I'm going to want to multiply both sides by 2. M is on both sides, so I can cancel out little m. Multiply both sides by 2, so we have 10/6 gm over r equals v squared. Cool. I can simplify this 10/6. It's kind of fun to do. That's going to be what, 5/3, if I can write. Gm over r equals v. And then I can just do good old square root. And we are in business. Awesome. Thank you so much for watching. I know that was, but it was also a whole lot of fun. So awesome. Good work, team.